A baby picture can reveal the blueprint for an entire life. The oldest light in our universe holds a similar secret. This ancient glow, called the cosmic microwave background, is a fossilized baby picture of the cosmos. It contains tiny patterns that are the direct seeds for every galaxy, star, and planet in existence. By the end of this video, you will understand how to read this cosmic blueprint and trace your own origins back to the first moments of time. We will uncover how microscopic ripples grew into the vast cosmic web, and why the universe looks the way it does today. What do you think it means to see the universe's first light? That brilliant fog was the entire cosmos in its earliest childhood. For hundreds of thousands of years, the universe was a sweltering, churning sea of particles and light, so thick that a photon of light could barely travel an inch before crashing into an electron. It was a cosmic traffic jam of unimaginable density. Then, in a pivotal moment, the universe expanded and cooled just enough for a profound change. Electrons slowed down and were captured by protons, forming the very first atoms of hydrogen and helium. In that instant, the cosmic fog cleared. The traffic jam vanished, and light, after being trapped for so long, was suddenly set free on a journey across the universe. This primordial flash of liberation is what we detect today as the cosmic microwave background. It is the leftover glow from that great clearing, now cooled and stretched by billions of years of expansion into a faint microwave whisper that permeates all of space. This discovery was one of science's great accidents. In 1965, two astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent, mysterious hiss in their giant radio antenna. They pointed it at the sky and the noise was there. They pointed it at New York City and the noise was there. They even famously cleaned out a buildup of pigeon droppings from the antenna, and still the hiss remained. This annoying, omnipresent static was, in fact, the echo of creation itself, the cooled remnant of the universe's first light. Their frustration earned them a Nobel Prize and provided the first direct evidence for the Big Bang. But this cosmic background is not perfectly smooth. If you could see it with microwave eyes, you would notice it is not a uniform sheet of light. It is imprinted with tiny, faint spots, regions that are ever so slightly warmer or cooler than their surroundings. These variations are mere millionths of a degree in temperature. Yet these imperfections are the most important features in the entire cosmos. They are the universe's original seeds of structure, the subtle ripples in the fabric of space-time that gravity would slowly, patiently sculpt into the galaxies and voids we see today. These faint ripples in the cosmic background are known as anisotropies. Think of a perfectly calm pond, its surface smooth and silent. Then, a single raindrop falls. The ripples that spread out from that impact define the entire surface of the water from that moment forward. The temperature fluctuations in the cosmic microwave background are the universe's version of those ripples. These are not random noise. They are a detailed pattern of minute differences in temperature, mere millionths of a degree, imprinted across the entire sky when the cosmos was only 380,000 years old. This pattern is the universe's original fingerprint. The great physicist Stephen Hawking once remarked that the universe does not allow perfection, and these anisotropies are the ultimate evidence of that profound truth. They are the cosmic imperfections from which everything we know was built. Each tiny hot spot you see on a map of the CBM is a region of the early universe that was ever so slightly denser and hotter than average. These were the cosmic overdensities, the places where gravity had just a little more material to work with. Conversely, the cold spots correspond to regions that were slightly emptier and cooler. It was from these minute differences in density that the entire story of structure formation began. Gravity is an amplifier of contrast. Over hundreds of millions of years, it patiently pulled matter toward these hot spots, the dense seeds. The slightly denser regions became even denser, beginning their slow, inevitable collapse into the first protogalaxies. The slightly emptier regions expanded into the vast cosmic voids we see today. So how do we translate this ancient map of hot and cold spots into a blueprint for our cosmic home? The first step is to measure these patterns with incredible precision, a task that requires the most sophisticated telescopes ever built, sent far beyond the interference of our own planet. To capture a whisper from the dawn of time, our tools must be almost impossibly sensitive. It is the astronomical equivalent of trying to hear a single snowflake land in a bustling city. This monumental task falls to a fleet of extraordinary observatories, each designed to listen to the universe's oldest story. On the ground, telescopes like the Atacama Cosmology Telescope in the high deserts of Chile and the South Pole Telescope at the frigid bottom of the world occupy some of the most remote and arid locations on Earth. Their positions high above the thick, moist lower atmosphere give them a clearer window, allowing them to stare intently at small, deep patches of the ancient sky. But to get the clearest possible view, we must go higher still, beyond the veil of our own atmosphere entirely. Space-based observatories provide the ultimate clarity. NASA Wilkinson Microwave Anisotropy Probe, or WMAP, was a pioneer, creating the first highly detailed full sky map of the cosmic background. But it was the European Space Agency's Planck satellite that truly delivered a portrait of stunning precision. Planck measured the temperature variations in the primordial light to within a few millionths of a degree, mapping the faint ripples with a clarity we had never before achieved. Yet these instruments do far more than just take a simple picture. They are sophisticated listeners, collecting data across multiple frequencies of light. Why is this so crucial? Our own Milky Way galaxy and everything in between glows with its own microwave light, creating a fog of foreground noise. By observing at many different frequencies, scientists can digitally subtract this galactic static, just as you might tune a radio to remove static and hear a distant station. This leaves behind only the pristine signal from the edge of time itself. The technological marvel of these missions gives us an exquisitely detailed view of the universe's infant face. This precise mapping is not an end in itself, it is the essential foundation. It provides the raw, undeniable data that fuels our theoretical models, the numbers that our equations must explain. With this incredibly detailed baby picture now in our hands, we are forced to ask a deeper question. What kind of physics, what fundamental forces in the newborn cosmos could have created such a specific and intricate pattern of seeds? That pristine signal from the Planck satellite reveals something astonishing about the infant cosmos. It was not a silent, still place. The early universe was a roaring cauldron filled with a symphony of sound. Think of a pot of water at a furious boil, with bubbles of sound expanding and colliding in a chaotic, energetic dance. In the hot, dense plasma of the newborn universe, sound waves were propagating outwards from every single one of those initial density seeds. For nearly 400,000 years, a cosmic tug-of-war played out. Photons of light, tightly coupled with particles of matter, exerted immense radiation pressure, pushing outwards like an explosive force. At the same time, the relentless pull of gravity worked to drag that matter back in. This created massive, spherical sound waves, ripples of compression and rarefaction that traveled at over half the speed of light through the primordial soup. Then, in the event we call recombination, the music stopped. The universe cooled, atoms formed, and the photons were suddenly set free. The tightly coupled plasma vanished, and the sound waves were instantly frozen in their tracks. The music of creation was silenced, and its final note was captured in the light. This process left a very specific signature, a kind of cosmic fossil. When we look at the pattern of hot and cold spots in the cosmic microwave background, we see a statistical preference for a certain size. There is a characteristic distance, an angular scale on the sky, where you are most likely to find a hot spot separated from a cold spot. This is the first acoustic peak. It is the imprint of the farthest distance one of those primordial sound waves could travel before the music stopped. This frozen echo acts as a fundamental ruler for the entire universe. By measuring the apparent size of this standard ruler on our sky, cosmologists can perform a profound calculation. They can deduce the actual geometry of the cosmos itself. Is the universe flat like a sheet of paper? Is it curved like a saddle? Or is it closed like a sphere? The size of these acoustic peaks provides the definitive answer. And this ruler does more than just measure shape. It allows us to take a cosmic inventory to weigh the contents of the entire universe without ever leaving our solar system. This cosmic ruler, defined by the first acoustic peak, does more than just confirm the universe is flat. It allows us to open the universe's recipe book and read the exact proportions of its fundamental ingredients. The specific patterns of hot and cold spots, their sizes and distributions, are like a complex barcode. When we scan this barcode with our theoretical models, it reveals a cosmic inventory so shocking it redefined our place in reality. The atoms that form every star, every planet, and every one of us, what we call ordinary matter, account for a mere 5% of the cosmos. We are not even the main ingredient. We are the rare, visible froth on a vast, dark ocean. Roughly 27% of the universe is composed of dark matter. This is the invisible cosmic scaffolding, the hidden skeleton whose gravity provided the essential pull to amplify those tiny primordial ripples into the first galaxies. Without this dark matter, the gravitational pull in the early universe would have been far too weak. The subtle density seeds would never have gathered enough material to ignite the first stars, leaving the cosmos a dark, formless void. The remaining 68%, the dominant component of the universe, is the most enigmatic of all dark energy. This is the force responsible for the accelerating expansion of space, a repulsive gravity that shapes the cosmos on the largest scales. How can we possibly know this from a pattern of ancient light? The answer lies in the fine details. The precise angular size of the first acoustic peak is exquisitely sensitive to the total density of the universe. A universe with more matter would have a different gravitational curvature, changing how we perceive the size of that frozen sound wave. The observed size fits only one specific cosmic recipe: a flat universe with exactly the right amount of total stuff to balance its geometry. The way smaller hot and cold spots are statistically distributed further fine-tunes this measurement, nailing down the individual contributions of normal matter, dark matter, and dark energy. This means the blueprint for our entire cosmic home, from the largest galaxy cluster to the smallest dwarf star, was written into the universe's first light. The stage was set not by the atoms we see, but by the immense, unseen gravitational presence of dark matter. This silent, invisible framework of dark matter was the universe's first construction crew. While the brilliant plasma of the Big Bang was still trapped in its chaotic dance with light, dark matter had already begun its work. Imagine two teams building a city on a vast, empty plain. One team, the normal matter, is trying to assemble bricks in the middle of a hurricane, constantly being blasted apart by fierce winds of radiation. The other team, dark matter, works in perfect silence and darkness, completely unaffected by the storm. They can lay the foundations, the roads, and the entire underground infrastructure without any interruption. This is the crucial advantage dark matter possessed. Because it does not interact with light or radiation, it felt no pressure, only gravity. From the very first moments, it could begin to collapse into subtle clumps and filaments, creating a vast, invisible scaffolding long before atoms could even form. The hot and cold spots we see in the cosmic microwave background are not just maps of matter. They are also shadow maps of this growing dark matter skeleton. In places where dark matter was already concentrating, its extra gravitational pull created slightly deeper wells, tugging a little harder on the ordinary matter and radiation. This enhanced the temperature differences we now observe, making the dense spots slightly denser and the voids slightly emptier. Why was this early start so vital? Gravity works slowly, especially across cosmic distances. If ordinary matter, hindered by radiation pressure, had to start from scratch after the universe cooled, there simply would not have been enough time in the age of the universe to form the colossal galaxy clusters and immense cosmic web we see today. The silent, relentless pull of dark matter's pre-built wells gave normal matter a massive head start. The blueprint in the light, therefore, carries the undeniable signature of an unseen architect. We cannot see dark matter directly, but we can see the profound gravitational imprint it left on the universe's very first portrait. This evidence tells us that the stage for all of cosmic history was set in the dark, long before the first star ever thought to shine. That silent, dark matter scaffolding provided the essential architecture for the universe's first great act of creation. For hundreds of millions of years after the CMB was released, the cosmos entered its dark ages, a time of profound blackness without a single star to pierce the endless night. But within that pervasive gloom, the subtle seeds from the cosmic background were slowly, relentlessly awakening. Guided by the gravitational pull of their invisible dark matter halos, vast pockets of pristine hydrogen and helium gas began to drift together. As these clouds contracted, a remarkable transformation began. The gas collapsed inward, piling onto itself, and in the resulting crush, the temperature at the core of these dense pockets soared to unimaginable extremes. This was the trigger for a cosmic revolution. When the core temperature reached millions of degrees, the immense pressure forced hydrogen nuclei to slam together, igniting the fire of nuclear fusion. In that brilliant flash, the very first stars were born. These first stars, known to astronomers as population 3 stars, were unlike anything in our modern night sky. They were colossal behemoths, likely hundreds of times more massive than our own sun. Think of our sun as a modest campfire, providing steady warmth for a planetary system. These first stars were like towering celestial infernos, raging with an intensity that is almost impossible to comprehend. They burned their hydrogen fuel at a ferocious rate, living lives of spectacular, brilliant brevity. A star like our sun will shine for billions of years, but these first giants blazed for only a few million years before meeting cataclysmic ends in titanic supernova explosions. Yet their short lives were not in vain. In their violent deaths, they performed the universe's first act of cosmic alchemy. The furnaces of their cores forged heavier elements like carbon, oxygen, and iron, which were then blasted out across space, seeding the primordial gas with the raw materials for future planets, oceans, and even life itself. Gravity, the great cosmic architect, did not stop with individual stars. It began weaving these brilliant new points of light into the first collective structures. Groups of these early stars, still swaddled in vast clouds of gas and dark matter, drew together to form the very first protogalaxies. These were the humble, building block beginnings of the majestic spirals and giant ellipticals we admire today. Our own Milky Way galaxy is likely a vast archaeological site, built up over billions of years from the mergers of countless such primordial fragments. The emergence of these first luminous objects did more than just decorate the void. It fundamentally changed the character of the cosmos. Their intense ultraviolet radiation began to blast through the surrounding neutral hydrogen gas, stripping electrons from atoms in a process known as reionization. This ended the cosmic dark ages, transforming the universe from an opaque fog back into the transparent, intergalactic medium we observe between galaxies today. Every step of this grand narrative, from the first flicker of starlight to the clearing of the cosmic fog, was a direct and inevitable consequence of the microscopic blueprint encoded in the cosmic microwave background. The journey from those faint quantum ripples to the first giant stars demonstrates a profound truth about our universe. The largest structures, the grandest of cosmic giants, have their origins in the smallest of beginnings. This timeline is a single, unbroken chain of cause and effect, a story written by gravity itself. It all begins at the 380,000-year mark, the moment the cosmic background radiation was set free. Astronomers call this the surface of last scattering, the final wall of light we can see before the universe becomes an opaque fog. From that moment, the cosmos plunged into its dark ages. For hundreds of millions of years, there was no light to see by, only the silent, relentless pull of dark matter. In the blackness, its invisible halos grew steadily, gathering mass and sculpting the foundations of everything to come. Then a cosmic dawn broke. Between 200 and 400 million years after the Big Bang, the first stars ignited. Their fierce, ultraviolet radiation acted like a cosmic firestorm, blasting through the neutral hydrogen gas that filled the universe. This epoch of reionization was a fundamental transformation, burning away the primordial fog and making the space between galaxies transparent once more. The universe was lighting its first candles and simultaneously cleaning its windows. By the time the universe reached its first billion years, the pace of construction accelerated dramatically. Those first small galaxies, drawn together by their immense dark matter anchors, began to collide and merge. This galactic cannibalism built larger, more complex structures. In the hearts of the most massive new galaxies, supermassive black holes awoke, gorging on vast amounts of gas and shining with unbelievable ferocity as the first quasars. These were the lighthouses of the young cosmos. Over the next several billion years, the universe wove its grandest tapestry. The subtle ripples from the cosmic background, amplified over eons, manifested on a scale almost too large to comprehend. The cosmic web emerged, a vast network of dark matter filaments stretching across the emptiness. Galaxies, like glittering jewels, were strung along these invisible threads, tracing out the hidden architecture of reality. Between the threads, immense cosmic voids expanded, creating the great empty deserts of space. Today, 13.8 billion years from the beginning, we live in a richly structured universe. We are part of a giant galaxy that is itself part of a massive cluster, which is just one node in an even larger supercluster. This entire hierarchy, from the smallest dwarf galaxy to the largest void, can be traced back in a direct, causal line to those specific temperature variations in the ancient light. The blueprint was always there, written in the first fire, and the story of our cosmos is simply the unfolding of that original, elegant design. Gravity is the universe's great storyteller, and its narrative is one of relentless amplification. That faint blueprint in the cosmic microwave background provided the opening lines, but gravity wrote the epic that followed. This process, known as gravitational instability, is a powerful feedback loop of creation. Picture a gentle hill on a vast, flat plain. Because it has just a little more height, and therefore a slightly stronger gravitational pull, it begins to attract loose soil from its surroundings. Over time, this makes the hill even taller, which in turn strengthens its pull, allowing it to gather even more material. The hill grows into a mountain. This is precisely what happened on a cosmic scale. Those tiny hotspots in the CMB, the regions of slight overdensity, were the universe's initial gentle hills. Their minute extra density gave them a minutely stronger gravitational field. This invisible pull began to gently tug on the surrounding dark matter and gas, drawing more material into the region. As more matter accumulated, the gravitational pull intensified, accelerating the process in a runaway cycle of collapse. The brilliant British physicist Sir James Jeans was the first to capture this process in mathematics. He revealed that for a small overdensity to grow, it had to be larger than a specific critical size, a value now known as the Jeans length. Think of it as a cosmic minimum order for gravity to start its work. If a fluctuation was smaller than this length, the outward pressure from radiation and heat would overwhelm gravity's weak pull, preventing collapse. In the searing heat of the very early universe, this Jeans length was astronomically large. Only the most massive ripples, the grandest of hills on the primordial plane, possessed the gravitational muscle to begin collapsing. This is why the largest structures in the cosmos, things like superclusters of galaxies, had to form first. They were the only fluctuations that could overcome the universal pressure. But as the universe expanded and cooled, a profound shift occurred. The cosmic pressure dropped. This caused the Jeans length to steadily shrink over billions of years. As this critical size decreased, smaller and smaller overdensities suddenly met the new, lower threshold for collapse. What began as the monolithic collapse of giant clouds now included the fragmentation of those clouds into smaller units. Vast protogalactic clouds, themselves products of the first great collapses, now broke apart into multiple, smaller galaxies. Within those galaxies, even smaller pockets of gas reached their own local Jeans length and collapsed to form individual star clusters and stars. This is the story of hierarchical structure formation. The universe built from the top down, with the largest scales assembling first, and then progressively smaller structures forming within them. This entire narrative, from the vast supercluster to the humble star, is written directly into the spectrum of the cosmic microwave background. The specific distribution of large, medium, and small hotspots in that ancient light predicts this exact sequence of events. Gravity's story is elegant and powerful, but a good mystery requires more than a compelling theory. It demands evidence, a way to check the story against reality. To truly test this gravitational blueprint, we must search for its echoes in the cosmos we see around us today. This grand narrative, stretching from quantum ripples to galactic superclusters, is more than a compelling story. It leaves a physical trace, a ghostly echo that we can detect in the emptiness of our modern sky. The patterns in that ancient light are not just fossils. They are the direct ancestors of the galaxies we chart today. To prove this lineage, scientists perform a kind of cosmic genealogy, comparing the universe's baby picture to a portrait of its adult self. They take the intricate map of the cosmic microwave background and cross-reference it with three-dimensional charts of the cosmos created by monumental surveys like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument. These projects have painstakingly mapped the precise locations of millions of galaxies, revealing the vast cosmic web in stunning detail. The result of this statistical comparison is nothing short of breathtaking. The regions of the sky that were subtly hotter and denser in the infant universe, those very same seeds, are statistically more likely to be overlain with a high concentration of galaxies in the present day. The gentle hills in the primordial landscape have indeed grown into the mountain ranges of the cosmic web, but the confirmation does not stop there. Remember the frozen sound waves, the Baryon acoustic oscillations. That characteristic size, the distance the sound could travel before the music stopped, also left its mark. When astronomers count pairs of galaxies, they find a subtle but undeniable statistical preference. There is a specific distance, about 500 million light-years, where you are slightly more likely to find two galaxies separated from one another. This is not a rigid shell around every galaxy, but a faint statistical echo, a whisper of that primordial rhythm still vibrating through the cosmos. This imprint acts as a fixed standard ruler billions of light-years long. By measuring how the apparent size of this ruler changes across different epochs of cosmic time, Scientists can trace the expansion history of the universe with extraordinary precision, probing the nature of the dark energy that drives it. This powerful correlation is the ultimate validation of our cosmic origins. It confirms, beyond a reasonable doubt, that the blueprint in the first light directly orchestrated the grand structure we inhabit. Yet this connection also reveals a more subtle interaction, a final way the ancient light speaks to us. As the photons from the cosmic microwave background travel for billions of years to reach our telescopes, their journey is not through empty space. They must pass through the evolving gravitational landscape of the growing cosmic web. The journey of that ancient light is a 13.8 billion-year odyssey through an evolving cosmos. Its path is not a straight line through empty space, but a winding route through the growing gravitational landscape of the cosmic web. Every filament of dark matter, every massive galaxy cluster it passes, exerts a subtle gravitational tug, gently bending the light's trajectory. This phenomenon, called gravitational lensing, leaves a unique fingerprint on the primordial light. It is as if we are looking at the universe's baby picture through a slightly warped sheet of glass, where the subtle distortions in the image are not flaws, but a hidden message. The pristine pattern of hot and cold spots we receive is minutely stretched and sheared, its original perfection ever so slightly scrambled by the gravity of everything that formed along the way. This lensing effect is incredibly faint, a distortion of just a few percent in the CMB's patterns. Yet, for cosmologists, it is a treasure map. By meticulously analyzing these minute deflections, they can perform a remarkable feat of cosmic cartography. They can trace the path of the light backwards and map the total distribution of mass, both dark and visible, that the light encountered during its epic voyage. We are effectively using the cosmic microwave background as a brilliant backlight, shining from the edge of the observable universe to illuminate the shadowy architecture of the cosmic web. The Planck satellite's map of this lensing potential is perhaps one of its most profound legacies. It provides a coarse, all-sky image of the dark matter distribution, a direct confirmation that this invisible scaffolding is truly there, woven throughout the cosmos in the exact way our models predicted. This signal is more than a static map. It is a movie of cosmic growth. Because the CMB light was emitted when the universe was a mere infant, and we observe it now, the lensing distortions capture the entire history of structure formation in between. They tell us how strongly the dark matter halos have condensed, and how rapidly the cosmic web has assembled over the last 13 billion years. This offers a unique and powerful test for our theories of gravity and the nature of dark matter. Does the observed growth of structure match what Einstein's theory predicts over these vast scales? The whispers of lensing in the ancient light suggest that our story is, for the most part, correct, but they also hint at new mysteries waiting to be solved. The temperature map of the cosmic background is only the first chapter of the story. The ancient light carries another, more subtle message, written in the direction of its vibrations. This property, called polarization, is a goldmine of information, revealing details about the universe's birth that temperature alone cannot. Think of the light from the CMB as a wave on a calm sea. The temperature tells us about the wave's height, whether it is a tall peak or a deep trough. Polarization, however, tells us about the direction the wave is wobbling. This polarization was imprinted during the final, frantic moments before the universe became transparent, as photons scattered for the last time off of free electrons. The pattern of this wobbling is not random. It is organized into two distinct types, which scientists call E modes and B modes. E mode polarization is the simpler of the two. It is generated by the same density fluctuations that created the hot and cold spots, the gentle hills and valleys in the primordial landscape. Because it is created in a different way, it provides an independent and often sharper confirmation of the conditions at recombination. It is like getting a second, higher-resolution photograph of the same baby, confirming every tiny feature we thought we saw in the first image. But the true holy grail of cosmology lies in the detection of the other type, the B-mode polarization. This signal is incredibly faint, a whisper within a whisper. Its existence points to two profound sources. The first is the gravitational shadow of all the structure that formed after the CMB was released. As the E-mode light traveled for billions of years, the gravitational pull of dark matter and galaxies warped its path, subtly twisting its polarization and converting some of it into a lensing B-mode. This is a fascinating echo, but the second source of B-modes is truly revolutionary. They could be a direct imprint of primordial gravitational waves, ripples in the very fabric of spacetime itself. These waves are not like sound waves moving through a medium. They are oscillations of space and time, theorized to have been generated during a fantastically violent event called inflation, a period of exponential expansion in the first fraction of a second after the Big Bang. Detecting this primordial B-mode signal would be like finding a fossil from the universe's very first instant of existence. It would open a direct window into energies and scales a trillion times more powerful than anything our particle colliders can reach, allowing us to test our theories about the fundamental forces at the moment of creation. This is the driving force behind incredibly sensitive experiments like the BICEP and Keck array telescopes at the South Pole, which stare at a pristine patch of sky through the frigid, dry Antarctic air, and the Future Light BIRD satellite, which we'll observe from the quiet of space. They are hunting for this ghostly signal, a faint swirl in the polarization of the oldest light, that could tell us what happened when the universe was born. The polarization of the cosmic microwave background adds a rich, new dimension to our cosmic narrative, connecting the growth of galaxies directly back to the universe's inflationary birth. This search for primordial gravitational waves brings us face to face with the theory that set the entire cosmic story in motion. The final, faint whisper in the ancient light brings us to the very beginning of everything. To understand the origin of those first cosmic seeds, we must journey back to a moment almost beyond comprehension, a fleeting fraction of a second after the universe began. This is the epoch of cosmic inflation, a theory that solves the deepest puzzles of our cosmos. Imagine a single subatomic speck of space, so small it defies all description. Then, in an unimaginably brief flash, this speck was stretched, its fabric expanding exponentially faster than the speed of light, until it became larger than our entire observable universe. This was not an explosion of matter into space, but a violent stretching of space itself. Within that furious expansion, something miraculous happened. The empty vacuum of this infant universe was not perfectly calm. It was fizzing with quantum uncertainty, a microscopic sea of virtual particles flickering in and out of existence. These are the quantum jitters, the fundamental fuzziness of reality at its smallest scales. As the fabric of space inflated at a fantastic rate, it stretched these fleeting quantum fluctuations, locking them into the very geometry of the cosmos. What was once a microscopic tremor became a macroscopic ripple in the density of the universe. The theorist Alan Guth famously described inflation as the ultimate free lunch, a mechanism that created the vast, structured cosmos we see today from almost nothing. These stretched quantum ripples are the direct ancestors of the hot and cold spots we see in the cosmic microwave background. They are the original density seeds, the imperfections from which gravity would later sculpt galaxies. This elegant theory makes two very specific predictions about the pattern of these seeds. First, it says the fluctuations should be nearly scale invariant. This means the statistical hills and valleys should look roughly the same whether you are examining a region the size of a supercluster or a single galaxy. It is a universal blueprint with no single scale favored over another. Second, It predicts these fluctuations should be Gaussian or random. There is no hidden order, no preferred spots on the sky, just the kind of pattern you would expect from the magnification of quantum chance. When scientists analyzed the exquisitely detailed map from the Planck satellite, they found both of these predictions confirmed with stunning accuracy. The statistical signature of the ancient light matches precisely what inflation foretold. This is why inflation is the foundational chapter of our cosmic story. It not only planted the seeds for all structure, but also explains the overall geometry of the universe. The reason the cosmos appears so remarkably flat on large scales is because inflation stretched it smooth, just as blowing up a balloon makes its surface appear flatter and flatter. This single, powerful idea from the first instant of time set the initial conditions for everything that followed, from the first star to the last galaxy. The specific size of those frozen sound waves acts as a perfect cosmic ruler. To understand why, picture a simple triangle drawn on different surfaces. On a flat sheet of paper, the angles of a triangle add up to exactly 180 degrees. But if you draw that same triangle on the surface of a sphere, a positively curved space, the angles will bulge outward, adding up to more than 180 degrees. Now, imagine this triangle is astronomically large, with its base formed by the characteristic size of the first acoustic peak in the cosmic microwave background, and its apex at our telescopes. The apparent size of that peak on our sky reveals the geometry of the space it traveled through. In a closed, spherical universe, light rays would converge, making the spots appear larger to us, like the bulging lines on a globe. In an open, saddle-shaped universe, light rays would diverge, making the spots appear smaller. The data from satellites like Planck delivers a verdict of stunning clarity. The spots are exactly the size predicted for a flat universe. The angles add up to 180 degrees. Parallel light rays on the grandest of scales stay perfectly parallel. This geometric flatness is a direct and beautiful confirmation of the inflationary paradigm. That frantic stretching in the universe's first moments would have smoothed out any initial curvature, just as blowing up a balloon to an immense size makes its surface appear locally flat. This measurement is not just about shape. It is a fundamental constraint on the cosmos's total energy density. A flat universe can only exist if the combined density of all its components, matter and energy, equals a very specific critical value. This precise geometric finding left cosmologists with an inescapable conclusion. The total amount of ordinary and dark matter we had measured only accounted for about 32% of what was needed. The remaining 68% had to be something else entirely. A mysterious component with repulsive gravity that drives the expansion of space to accelerate. We call this dark energy. So, the flatness of the universe, read from the ancient light, did more than confirm a theory from the first instant. It unveiled the dominant force shaping the cosmos's ultimate fate. Dark energy is the final, decisive character in our cosmic story. For billions of years, gravity reigned supreme, patiently sculpting the grand tapestry of the cosmic web from the faint seeds in the ancient light. But around 5 billion years ago, a cosmic tipping point was reached. The universe had expanded so much that the density of matter, both dark and visible, dropped to a critical low. It was at this moment that dark energy, a mysterious repulsive force inherent to the fabric of space itself, emerged from the shadows to take command. Think of a master sculptor meticulously building a vast, intricate sandcastle. For eons, the sculptor works undisturbed, piling sand higher and higher. Then the tide begins to rise. A gentle, inexorable force of water slowly seeps into the sand, making it harder to build, and eventually threatening to wash the entire structure away. Dark energy is that cosmic tide. It does not destroy existing structures like your local galaxy cluster, which are bound by their own strong gravity. Instead, it opposes the formation of new, larger structures. It stretches the very space between galaxy clusters, making it more difficult for gravity to pull them together. How can we possibly see this effect from our tiny vantage point? The answer lies in comparing the universe's blueprint with its final construction. The cosmic microwave background gives us a precise measurement of the initial amplitude of those primordial ripples. It tells us exactly how much raw material gravity had to work with at the beginning. We then use massive galaxy surveys to take a census of the cosmic web in the modern universe, measuring how much those initial ripples have actually grown. The result is a profound discrepancy. The large-scale structures we see today are slightly smaller, slightly less clustered, than they should be if gravity had been working alone for 13.8 billion years. Something has been applying a subtle brake on the growth of the cosmos, and that something is dark energy. This signature is etched into the vast, empty voids between the galaxies. These cosmic deserts are expanding faster than the rest of the universe, pushed apart by the repulsive force of dark energy, which further stifles the ability of matter to bridge the gaps. The ancient light provides a second, independent line of evidence for this cosmic acceleration. The precise pattern of hot and cold spots allows scientists to calculate the distance to the surface of last scattering with incredible accuracy. That distance is simply too great for a universe that has been slowing down under its own gravity. The only way the light could have traveled that far to reach us is if the expansion of space has been accelerating, stretching the journey and the very waves of the light itself. So the cosmic microwave background does more than just show us the seeds of everything. It also reveals the force that will ultimately determine the fate of everything. This complete history, from explosive birth to its accelerating maturity, allows us to project the story forward to its final, quiet chapters. This long-term forecast paints a picture of a cosmos in quiet retreat. Armed with the precise initial conditions from the cosmic microwave background and the measured strength of dark energy, we can project the evolution of the cosmic web billions of years into the future. The story shifts from one of construction to one of isolation. Local galactic neighborhoods, like our own Milky Way and its eventual merger with the Andromeda Galaxy, will remain gravitationally bound, forming a single, larger island universe. But on scales beyond these local groups, a profound change will unfold. The relentless accelerated expansion driven by dark energy will stretch the very fabric of the cosmic web. Those magnificent filaments of dark matter that connect galaxy clusters will be pulled taut, then begin to snap. The great cosmic metropolis, once bustling with interacting clusters, will slowly empty out. Galaxy clusters will become isolated archipelagos in an ever-darkening and expanding sea of nothingness, their gravitational bonds unable to overcome the growing cosmic repulsion. The growth of structure, which began with those faint ripples in the first light, will not just stop. It will reverse on the largest scales. The vast superclusters that span hundreds of millions of light years will be gently, inexorably pulled apart. For any potential observers in the far future, the universe would appear profoundly different, a much simpler and more diffuse place, devoid of the intricate web we are privileged to see today. This entire destiny is written directly into the parameters we measured from the ancient light. It reveals a humbling truth. The rich cosmic tapestry we study is not a permanent fixture, but a transient, brilliant phase in the long life of the universe. We exist during a golden age of cosmic structure, a window of time when the universe is complex enough to build galaxies, stars, and planets, yet still young enough for those structures to be connected and visible. This realization forces us to confront our own fleeting moment in this grand, evolving narrative, and to appreciate the incredible fortune of our timing. This ancient light is our ultimate time machine, a portal to the universe's formative years. Studying it is a form of cosmic archaeology, where we are not digging through layers of soil, but through layers of time itself. Just as an archaeologist pieces together fragments of pottery to reconstruct an ancient civilization, a cosmologist pieces together the statistical patterns in this light to reconstruct the laws and conditions of the primordial cosmos. The primary tool for this excavation is a graph known as the CMB Power Spectrum. This is not a picture of the sky, but a mathematical fingerprint that summarizes the relative strength of the hot and cold spots at every possible size. Each bump and wiggle on this graph is a direct message from the dawn of time. The first major peak, the one we identified as the frozen sound wave, confirms the universe's flat geometry. The second peak is a direct measure of the density of ordinary matter, the baryons that make up our world. It tells us how much stuff was in the cosmic plasma to slosh around and create those pressure waves. The third peak, and those that follow, are even more revealing. Their precise heights and positions are exquisitely sensitive to the presence and behavior of dark matter. Because dark matter does not interact with light, it does not create pressure. Its gravity, however, subtly alters the rhythm of those primordial sound waves, leaving a distinct signature in these higher peaks that we can decode. By creating sophisticated computer models of the early universe and adjusting their parameters, we can run a cosmic matching game. We tweak the amounts of dark matter, dark energy, and the initial density of the universe until our model's predicted power spectrum perfectly overlays the one we actually measured from the Planck satellite. When the lines match, we have found our universe's recipe. This is how we know the cosmos is 13.8 billion years old, and that it is composed of 5% ordinary matter, 27% dark matter, and 68% dark energy, all with an accuracy of better than 1%. This rigorous, quantitative approach makes the cosmic microwave background the single most important piece of evidence for our standard model of cosmology. It is the foundational text, the Rosetta Stone that allows us to read the entire history of the cosmos, from its first quantum whisper to its current grand design. Yet this cosmic blueprint, for all its stunning precision, holds a few faint smudges that defy simple explanation. The data from Planck and other observatories is not perfectly uniform. It contains subtle anomalies, features that do not quite fit the elegant simplicity of our standard model. One of the most intriguing is the dipole asymmetry. When scientists analyzed the map, they found that the temperature fluctuations in one hemisphere of the sky are slightly stronger, more pronounced than those in the opposite hemisphere. It is as if one half of the universe's baby picture was developed with a slightly higher contrast than the other. This should not happen according to our foundational principle that the cosmos is the same in every direction. Another puzzle is the famous cold spot. This is an unusually large and profoundly cold region on the map, a vast circular patch that is significantly cooler than our models predict. Some have theorized it could be the shadow of a cosmic supervoid, an immense and mostly empty region of space that the ancient light passed through. Others have proposed even more exotic ideas, suggesting it might be the imprint of a cosmic texture, a defect in the fabric of spacetime left over from a phase transition in the very early universe. Perhaps the most philosophically troubling anomaly is what some researchers half-jokingly call the axis of evil. This refers to a strange alignment of the very largest scale patterns in the cosmic microwave background. These biggest ripples appear to be coordinated, pointing in a preferred direction across the sky. This again challenges the cosmological principle, the core idea that the universe has no special place or direction. Now, it is entirely possible that these are all just statistical flukes. When you look at any complex set of data, you are bound to find a few oddities that appear significant just by random chance. They could also be subtle artifacts from our own galactic neighborhood, a kind of foreground smog we have not perfectly accounted for, but their persistence is a powerful motivator. They are the loose threads in the cosmic tapestry, and scientists are compelled to pull on them. These anomalies drive the development of the next generation of telescopes and satellites, missions that will measure the polarization of the ancient light with even greater fidelity. They inspire theorists to explore more complex versions of inflation and to hunt for exotic relics from the first moments of time. The presence of these cosmic curiosities does not invalidate our profound understanding. Instead, it reminds us that every great discovery opens the door to deeper, more fundamental questions, ensuring that the story of our origins is still being written. These faint anomalies in the ancient light are not dead ends, but signposts pointing toward a more profound truth. To follow them, we need a new generation of eyes, instruments of almost unimaginable sensitivity designed to listen even more closely to the universe's first whisper. The quest continues with an ambitious slate of future experiments, each pushing the boundaries of what we can perceive. High in the Chilean Andes, the Simons Observatory is currently taking shape. This formidable ground-based facility will deploy hundreds of thousands of tiny, superconducting detectors across multiple telescopes. Its primary mission is to measure the polarization of the cosmic microwave background with a sensitivity that dwarfs all previous efforts, bringing the hunt for the elusive primordial B-mode signal into sharp focus. This is like trying to measure the gentle distortion of a pond's surface from a single raindrop that fell miles away. The Simons Observatory will give us the precision to see that tiny ripple. Looking further ahead, the CMBS-4 project envisions a coordinated global network of telescopes, both at the South Pole and in Chile, working in concert. With orders of magnitude more detectors, this endeavor aims to scan the sky for so long and so deeply that it will definitively detect or rule out a large class of inflationary models. It will tell us, once and for all, whether the primordial gravitational wave signal is there, hiding just below our current threshold of perception. But to get the clearest possible view, free from all atmospheric interference, we must return to the quiet of space. Proposed missions like the European-led CORE+ are designed to do just that. This satellite would provide a full-sky, multi-frequency map of the CMB, with vastly improved resolution and sensitivity over what Planck achieved. Imagine looking at a beloved, yet grainy, historical photograph, and then being handed a modern high-definition version where every detail is suddenly crisp and clear. That is the leap in clarity these missions promise. These next-generation instruments will do more than just refine the numbers in our cosmic recipe book. They will open entirely new windows into the physics of the very early universe. Could there have been multiple fields at play during inflation, creating a more complex symphony of ripples than we currently assume? What can the subtle ways the CMB light is stretched tell us about the absolute masses of neutrinos, the ghostly particles that flow through us by the trillions each second? The future of cosmic microwave background science is not merely about confirming what we think we know. It is about discovering the questions we have not yet even learned to ask, deepening our connection to the moment of creation itself. Even the faintest cosmic ghosts leave a shadow. The ancient light of the cosmic microwave background is so sensitive, it even records the passage of the universe's most elusive particles, neutrinos. In the very first second after the Big Bang, the cosmos was filled with a dense, searing ocean of these particles, streaming freely at nearly light speed. Think of them as a cosmic wind, blowing through the primordial plasma. This wind had a subtle but profound effect. While gravity was trying to pull matter together into the first clumps, this relentless stream of neutrinos was pushing back, creating a kind of friction or radiation drag that made it harder for the smallest structures to form. It was like trying to build delicate sandcastles in a strong, constant breeze. The smallest piles of sand, the tiniest cosmic ripples, were the most easily swept away. This ghostly influence left a specific signature in the music of the spheres. When we look at the CMB Power Spectrum, the graph that charts the strength of the hot and cold spots, we see its echo. The very highest acoustic peaks, which correspond to the smallest ripples in the early universe, are slightly dampened. They are not as tall as they would be if this neutrino wind had never blown. By measuring this precise damping effect, cosmologists can perform a remarkable feat. They can weigh a ghost. The amount of suppression tells us that the combined mass of all three known types of neutrinos must be astonishingly small, less than about 0.12 electron volts. To put that in perspective, a single electron volt is a unit of energy so tiny that a common mosquito in flight has about 1 trillion times more energy. This limit, derived from the ancient sky, is a powerful check on the physics happening in our deepest underground laboratories. It confirms that the universe itself acts as the ultimate particle detector, preserving a fossil record of these ghostly particles and revealing how they helped sculpt the cosmic landscape we inherit today. That frozen sound wave from the dawn of time gives us more than a story of our origins. It hands us a tool. The characteristic size of those Baryon acoustic oscillations, a span of about 500 million light-years, became a permanent fixture woven into the fabric of the cosmos. This scale acts as a cosmic standard ruler, an indelible mark on the universe that we can use to measure its growth across billions of years. The incredible part is that this same ruler, first seen in the infant universe's light, is also stamped onto the distribution of galaxies we see around us today. When astronomers create three-dimensional maps of the cosmos, they find that galaxies are slightly more likely to be separated by this specific distance. It is a faint statistical echo of that primordial rhythm, a ghostly shell of preference that surrounds every point in the cosmic web. How does this become a measure of expansion? Think of a ruler painted on a rubber sheet. If you stretch the sheet, the ruler itself stretches and the markings become farther apart. But our cosmic ruler is different. Its physical size, the actual 500 million light-years, is fixed in stone, set by the physics of the early universe. It cannot stretch. So, as the universe expands, the only thing that changes is how big that fixed ruler appears to be from our perspective. By looking at galaxies that are nearby, we can measure the apparent angular size of this standard ruler. Then, we look much deeper into space, at galaxies so far away their light has been traveling for billions of years, and we measure the ruler's apparent size at that earlier cosmic epoch. If the universe has been expanding at a constant rate, the ruler will appear to shrink in angular size in a predictable way as we look farther away. But if the expansion has been speeding up or slowing down, the apparent size of the ruler will deviate from that prediction in a specific way. This makes the Baryon acoustic oscillation technique incredibly powerful for probing dark energy. Unlike methods that rely on the perceived brightness of objects like supernova, which can be dimmed by interstellar dust, the BAO method relies purely on geometry. It is a direct measurement of the universe's stretching, using a ruler we know to be true. This is the driving force behind monumental galaxy surveys like the Dark Energy Spectroscopic Instrument, or DESI, which is meticulously cataloging the positions of tens of millions of galaxies. By applying this cosmic tape measure across different slices of time, these projects are tracing the history of the universe's expansion with breathtaking precision. The stunning coherence of seeing the same 500 million light-year scale in both the ancient cosmic microwave background and in the modern galaxy distribution is a profound validation. It tells us that the same physics that governed the universe's first cry also orchestrates the grand expansion we witness today, connecting the past to the present with a single, elegant measurement. That seemingly random map of hot and cold spots is actually a complex cosmic chord, a single, sustained note played by the infant universe. To understand its meaning, we must break this chord apart and identify its individual notes. Cosmologists achieve this through a powerful mathematical lens known as harmonic analysis. Think of the entire sky as a giant, spherical musical instrument, like a celestial bell that was struck once, long ago. The pattern of temperature variations is the intricate vibration left on its surface. Harmonic analysis is the tool that lets us listen to each individual frequency of that vibration separately. It decomposes the sky's mottled pattern into a set of fundamental waves called spherical harmonics. You can picture these as the distinct, resonant notes the spherical bell can naturally produce, each one a specific, graceful pattern of hills and valleys sweeping across the celestial sphere. Each of these harmonic modes is labeled by two numbers, L and M. The number L essentially tells you the angular size of the fluctuation. A mode with a low L value corresponds to a very large, gentle wave stretching across the sky, while a high L value represents a much smaller, tighter ripple. It is the difference between the deep, fundamental hum of the bell and its high-pitched, intricate jingles. When we calculate the average amplitude or strength of all the fluctuations at each possible angular scale, we create the most important graph in modern cosmology, the CMB Power Spectrum. This plot is not a picture. It is the universe's genetic code translated into a mathematical form. The power spectrum reveals a series of clear, resonant peaks, and each peak is a direct echo of the universe's early symphony. The first towering peak is the fundamental harmonic. Its position tells us the angular size of the sound horizon at the moment of recombination, that frozen instant when the music stopped. This is our fundamental cosmic ruler. The second peak is the first overtone, a harmonic that resonates with the density of ordinary matter, the baryons that were sloshing back and forth in the primordial plasma. The third peak and those that follow are even more revealing, as their precise heights are exquisitely sensitive to the amount and behavior of dark matter, which influence the rhythm of the waves through its gravity alone. The precise heights and positions of all these peaks lock in the values for the cosmic ingredients with breathtaking accuracy. This mathematical framework transforms a beautiful but mysterious image into a rigorous, quantitative test of our physical theories. It allows us to measure the universe's age, its geometry, and its contents not as rough estimates, but as precise numbers derived from the primordial vibrations of space itself, testing the very laws of physics against the backdrop of creation. This cosmic blueprint is more than a historical record. It is a ruthless judge of new ideas in physics. The exquisitely detailed pattern of the cosmic microwave background acts as a universal litmus test, confronting every bold new theory with a simple, direct question. Can you recreate this specific fingerprint of the infant cosmos? Any proposed modification to our understanding of gravity, such as theories that suggest a tweak to Newtonian dynamics without dark matter, must stand before this data. These ideas must explain not only the rotation of galaxies today, but also the precise arrangement of acoustic peaks and the specific pattern of polarization imprinted when the universe was only 380,000 years old. So far, the standard model of cosmology, with its 6 fundamental parameters describing dark energy, dark matter, and ordinary matter, reproduces the CMB power spectrum with breathtaking accuracy. This fit is a monumental achievement, but it also raises the bar impossibly high for any challenger. Even more exotic proposals from the frontiers of theoretical physics are put to the test. Concepts emerging from string theory or quantum gravity that predict new, lightweight particles or subtle wrinkles in the fabric of spacetime from the inflationary epoch must also face the cold, hard reality of the Planck satellite's maps. These theories often suggest slight deviations in the way the largest scales in the CMB should appear, or they might predict a specific, non-random pattern in the polarization that we have not yet detected. The fact that we have not seen these clear signals places severe constraints on what is possible, ruling out entire families of theoretical ideas. This transforms the entire observable universe into the most grand laboratory imaginable. We are no longer confined to testing physics in underground tunnels or massive particle colliders. We can now use the cosmos itself as a high-energy physics experiment, one that has been running for 13.8 billion years. The ancient light's legacy is therefore dual in nature. It provides a stunningly clear picture of our past, but it also serves as an essential guide for the future, pointing theorists toward which mathematical paths are still possible through the rugged landscape of reality and which are now forever closed. This scientific narrative is not locked away in private archives. The monumental effort to map the cosmic microwave background has forged a powerful legacy of open data, a gift to the entire world. After a short period where the mission teams conduct their initial analysis, the floodgates open. Space missions like WMAP and Planck release their complete data sets, along with the sophisticated software tools needed to read them, to the public. This act transforms a single experiment into a global resource. Suddenly, thousands of researchers, from a graduate student working on a new theory to a senior cosmologist at a major university, can access the same raw data. They can perform their own independent analyses, test novel ideas, and cross-check every published result. This process is the bedrock of scientific integrity, ensuring that the profound conclusions about our universe are not the product of one team's work, but a consensus built on a foundation of transparent, verifiable evidence. The iconic full sky maps themselves have transcended their scientific origins to become cultural touchstones. You have likely seen them in documentaries, on the pages of textbooks, or even interpreted as works of art. They represent more than data. They are a symbol of humanity's collective curiosity and our deepest look back into the cradle of time. Educational programs and planetarium shows built around this data demystify the methods of modern cosmology, allowing students and the public to grasp the wonders of our cosmic origins. This collaborative open science model demonstrates how monumental scientific endeavors can and should operate. It turns a highly specialized measurement into a universal tool for discovery, a shared inheritance that invites everyone to participate in unraveling the story of the universe. This public legacy guarantees that the secrets whispered by the first light remain a narrative for all of humanity to explore and cherish. This ancient glow is our shared origin story, written across the sky. Our journey through this primordial light has revealed a cosmos born not in chaos, but from the subtle amplification of quantum whispers. We have traced a direct, unbroken line from those microscopic ripples in spacetime to the vast galactic cities and the planets that orbit their stars. This narrative connects your own existence to the universe's first fiery moments, anchoring our place in a grand, cosmic lineage. The cosmic microwave background stands as one of the great pillars of modern science, a precise celestial ledger that has given us the universe's exact age, its startlingly flat geometry, and the definitive recipe of its dark and visible ingredients. Yet, for all its clarity, it does not offer finality. It generously leaves us with tantalizing anomalies, cosmic curiosities that challenge our most fundamental assumptions and propel us toward the next great discovery. As we look to the future, to missions that will listen even more closely to this ancient whisper, we are left with a profound and humbling realization. In studying the universe's oldest light, we are not merely exploring distant physics. We are reading our own cosmic ancestry, a family history written in the language of light, gravity, and time. Let this knowledge settle in, the understanding that the same forces that sculpted galaxies also forged the very atoms within you. What does this cosmic connection inspire in you? Share your reflections in the comments below, and subscribe to join us as we continue to unravel the deepest mysteries of the universe together.